All right, we were just talking about selection processes. Okay, so stepwise selection in multiple regression, it's selecting a model by automatically adding or removing individual predictors one step at a time, hence stepwise, based on their statistical significance. For example, commonly you may set it at a p-value of less than 0.15. And so then that helps you develop that model that you're trying to predict, and you make it very parsimonious so that you just have enough models, variables in there to predict the outcome. You also can control the details of this process, and you can, including how you change what is for including variables within the model. And you can add or remove things. Sometimes it's like a bad Sudoku puzzle. And sometimes you may even keep variables in a model because you want to adjust or control for that, even if you had a p-value greater than 0.15. The important part of this is, when I'm explaining this to you, is that when you're reading a research paper and they do multiple regression, they need to provide enough details so you understand how they did what they did, how they selected their variables. Sometimes that is not always presented in manuscripts. Sometimes it may be due to the style of the journal. But it is important information, I do think, to include. So when they're doing multiple regression, they do t-distributions when they're looking at individual differences in individual parameter estimates. When you have larger degrees of freedom, basically that equates to more subjects in a sample. And what it's trying to do is it's a probability distribution that is theoretically resembles a normal distribution, as you can see here. And if it's significant, the rejection, and it's in the rejection regions, then we reject the null and we accept the alternative hypothesis. All right, so now let's go through an example. This was a something I pulled off the internet. So what they have here in this particular model is they are trying to predict math scores from reading score, female gender, and social studies. And I'm sorry, they're trying to predict science scores from reading scores, gender, social studies scores, and a math score. Okay, this is where you can include a female gender in here. And probably what they did was they coded female gender as 1, and then a 0 would be male. So that's what it's being referred to in the analysis. And so what they first do is they do an ANOVA, which is uses the F-test. That's the first thing you're going to look at. And so that's that table in the middle. And what we can see there is that it is statistically significant. Right here. And then so then the next step you would do is you go look at and see which variables are related to y, which of our parameter estimates were significant. So what you're going to go and look at is you're going to look at the standardized coefficients here. And this is showing you for every 1 unit change that we were talking about earlier. Here's the t results for each one of those for math, female gender, social studies, and reading score. If I look at this table, I know that all but that math score and reading score are significant. These other two are not, because the t-score is less than 2. So that's a good rule of thumb to remember with that. You can see the corresponding p-values here, and then the 95% confidence intervals here. This crosses over, and so I also know that this is not statistically significant, so it's in that negative range with that confidence interval. Then you're going to look at and say, okay, I found out that that those predictors, the model a good fit? And that's where I look at the adjusted R squared, and this adjusts for the number. It penalizes you for additional predictors, so you can see an R squared here, and then this one's a little more conservative of a result. So that's telling us that 48% of the variance in science scores is predicted by our model with these variables included. So there's some key assumptions you need to know about. Is there a linear relationship? If there's not one, why do it? Normality. Is the population of Y values for each predictor, are they normally distributed? Do they have equal variances, that homoscedasticity that we talked about earlier? Are they independent? The observations of those XY pairs, are they separate and independent? Is there a lack of correlation or multicollinearity between independent variables? If many of your independent variables are highly correlated, you need to go back. You're going to have some problems with your model. You'll need to remove one or more or make some adjustments. Now, I put this in there just to give you an idea of the steps that go into any sort of multiple regression analysis. The first thing is you're selecting your variables, and we talked about doing stepwise regression analysis. Then we're going to refine our model, and maybe we may put variables in, pull them out. Looking at our assumptions, we're going to make sure that we're addressing those. And if we have some errors, sometimes if you have outliers, or maybe when somebody entered the data in, there's a typo. And what that does is it creates problems with the analysis, and you have to go back and fix those. And there are some ways with the software to help you identify those variables. And then what you can later on do is you go down and you can actually validate your statistical model. So the key is there's got to be a linear relationship. You don't want to extrapolate beyond those range of values. The regression coefficients represent the mean change in the outcome variable for every 1 unit change in the predictor. Inclusion of multiple predictors allows you to adjust or statistically control for the effect of the other predictors on the outcome. And you can also look at model fit with the R squared. So say, for example, if you have an R squared of 89%, that's pretty darn good. That's very good model fit for predicting that particular outcome. So when we're using regression to predict the future, you got the same assumptions as the conditions are the same in the future as they are now. Remember, correlation does not equal causation. Finding an association is only the first step in really establishing causality. You also have to sometimes adjust when you're doing multiple tests. You have to adjust your confidence intervals sometimes.